Hello and welcome to today's video on Q-learning with a Q table. So let's start off and talk about what that is, maybe and why you should care, why we're building this today. So if you've done any reinforcement learning, the place that you probably started was with Q-learning. Q-learning is usually a pretty basic, you have a neural network and you are estimating the value of an action in a given state. So if my agent, my player, is right here, you're estimating the value of the action of moving to this other state, which is over here. And then the idea is that over time, the network learns what the values of the various states are, including, the value of getting to the prize at the end, which is usually awarded as a 1. And then as it learns the values of those states, it's able to predict the values and thus guide the agent towards the end goal. Q-learning or Q-learning with a Q table, and I'm going to borrow something from Free Code Camp over here, just to use our description or their table graphic. Q-learning with a Q table is basically the same approach, except instead of having a neural network that's estimating the values of those various states, you build code that builds up a Q table of what those various state action pairs are and what their values are. So basically, what we do is instead of the neural network seeing, hey, this is a 1, and then trying to figure out what actions led to it, we're just saying, hey, this had a value of 1, and on the next pass, where our player gets here, we're going to say this has a value of 0.9, and this has a value of 0.8, and this has a value of 0.7. And so on. And then that approach allows the player to slowly get to our target state. And so let's talk about the why. There are obviously more modern methods of doing this. There are, there's lots of information out there about that. I think going through a traditional Q table approach kind of helps break down the problem and helps build some intuition around what Q-learning is actually doing for you and how these pieces fit together. It was also a little bit of a personal challenge for me to sit down and do this without a reference, without looking at the equations behind it, and without AI. So just to kind of say, hey, I understand the principles. Let me sit down and see if I can put something together that approximates a Q table implementation. So that is what we're doing today. All right, let's go ahead and get started. So I am in NeoVim. You don't have to be. I am in the middle of a 2-week Vim challenge. So I'm going to go ahead, and you can follow along in any IDE you'd like. The only requirement is that you have Python and you are comfortable using pip. So I'm going to go ahead and create a requirements.txt for this project. And in that requirements.txt, we are going to put gymnasium. We're going to put gymnasium toy text, because this is a toy text environment. And we are going to put NumPy. Okay, so we're going to save that out. And I'm just going to do a pip install -r requirements.txt, and now I have my requirements. I already had them. I was working in this environment, but now you have your requirements. So let's go ahead and we are going to create a main.py, and that main.py is going to be our primary place to build out this code. There's no need for a second file. This is a pretty simple implementation, and we're going to put the training and the test in the same file because it's so fast. And also, let me go ahead. There's zero reason for me to have that sidebar, and I can give us a little bit of extra zoom without it. Yeah, that ought to be really easy to see. Okay, cool. Let's go ahead and get started. So the first thing we're going to do is import gymnasium as gym. We're going to import time, and we're going to import numpy as np. We need to make the environment, so that syntax is pretty simple. That's going to be env equals gym.make, and we are going to make Frozen Lake v1. We will do a map name of 4x4. We'll do is slippery, is false, and render mode is human. All right. And let's just go ahead and get a random, actually first I'm just going to run it. We'll do, yep, cool. No errors. First thing we're going to do then is go ahead and just play a game, play around, and see if, just see the game run, so you can kind of see what we're dealing with. So we're going to set done is equal to false, and then we'll say while not done, and then action will be equal to env.actionSpace.sample. That's something that Gym gives you by default. So that's going to take a sample of valid actions in a given state. And then we will just call our step. So next state reward done truncated info equals env.step action. And then we will just set, we'll go ahead and set state up here to none, and then state is equal to next state. And we don't actually need that yet. Again, we're just doing random actions, but that is something that we'll want later. All right. It doesn't like that we did not call reset first. That is totally true. So we're just going to say env, oh, no, you go full screen. env.reset state info equals. All right, now we should be ready to play. All right, and it's quite small. I actually don't know how to make the game bigger, but that gives you an idea of what we're doing. And let's go ahead, and I'm just going to wrap this. We'll go ahead and do episodes equals, we'll do 10. 10 episodes seems fair. All right, and then we can say for episode in range episodes. Okay. Tab that in. And now we're basically just playing 10 times, which gives us a little bit of an easier view. And you can see right now our little player is playing pretty randomly. I guess he occasionally gets out past the lake that he's falling into, but for the most part, he's just crashing very, very quickly because he's not working off of any kind of intelligence. So now we get to start building the intelligence into the process. So let's start out with our Q table. And I am actually going to set episodes to 1 because I don't want to edit the code too much, but I do want to focus more on the Q table side of things for a minute. So we're going to do Q table is equal to np.zeros. And we're going to do 16, 4. All right, so let's talk about what we're doing. So we're creating a a Q table, and table in the literal sense, like a spreadsheet table. You can think of it that way. It's going to be 16 long and 4 wide. And we're doing that because that is the number of states by actions. So there are 16 total states we could be in, 4 by 4. And in each state, we could have up to 4 actions. So every row of a Q table is going to represent one of these squares. Every column of a Q table is going to represent action. You'll note that we don't actually have to create a real map of the environment. That kind of spatial configuration isn't really necessary here. We just have to create a list of states and a list of environments, and that is what we have here. So if I'm just going to print Q table just to give us sort of an early view. And there's our Q table. So right now it's a whole bunch of zeros. So what we need to do is we need to start to fill that Q table in to build some intelligence into this process. So we're going to define a few variables up with episodes. And the first one is going to be, and these are things that get traditionally called this way. We're going to do gamma as 0.9, and that is the discount factor. So at a super high level, the value of a state, let's just map this out before we keep going. So the value of a state action pair, which you'll frequently see as Q S of A, is how that's normally defined, is equivalent to the discount factor times the value of the next state. So Q S1 A1, S1 of A. So the next state, and then plus the value of the current state. So what you're basically saying is we want to say that the current state has whatever value it has, and then it's also basing its value on the value of the next state. That's probably a bad description mathematically, but it's basically what's happening here. So whatever again, going back to our game here, so let's say this has a value of, we won't even use decimals, we'll say this has a value of 100, well then this has a value of 99, and this has a value of 98, 97, 96, 95, and so on. And then as it values those actions, it gives it something that it can use to move towards the goal. So what we have to do is help our code learn those actions and values. So that's what we're going to be doing. So gamma is the discount factor. It's how much less the next state is valued than the previous state is valued than the next state. It's basically saying, hey, this is only going to be X amount of the next state, because otherwise what you would end up with is a table of ones. And it's already kind of going to get close to that, but they will always be, in some kind of sloping order, which will help show it where to go. So we have our gamma, we have our alpha, which is our epsilon decay. We'll talk about epsilon in a moment. We've already got episodes. We will go ahead and do epsilon equals 1, and min epsilon is equal to 0.1. And again, if you haven't hit this concept, we will talk about it here. So epsilon, we're going to be using something called epsilon greedy action selection. So epsilon greedy basically just means that we're going to take we're going to have a value, in this case epsilon, that's going to slowly decay. And if a random number is under that value, we're going to take a random action, or we're going to take a non-random action versus a random action. That sounded complex, but really all it means is that a percentage of the time we are going to take random actions and explore the space, and then another percentage of the time we are going to take deterministic actions and follow the Q table. And then at the beginning, since this is a ratio, at the beginning we are going to take 100% random actions. We are going to slowly move towards 10% random actions, and we are going to do that. We're going to make that slope, that change of epsilon, based on this alpha value, which can be tweaked and played with, and you should. All right, so let's go ahead and put that into practice. So while not done, action space sample, we're going to tweak this just a little bit. We're going to say if epsilon is less than np.random.rand. And I should say at the beginning I talked about building this out without a reference. What I was talking about specifically is without a reference for the implementation. Obviously I did not type out the Frozen Lake gym.make command from memory. That didn't happen. But, it was the overall implementation was a from memory. Very, very useful to take the time to, and I think this is a good mental exercise if you are using a lot of AI in your day-to-day programming. I think it's really, really useful to take the time to go back and read some of the docs around some of these things. What does np.random.rand give you? What is the difference between np-max and np-argmax? I think we use these things all the time, but when you're sitting down and doing it from memory, it can be really helpful to go, hey, yeah, let me go read the doc and see exactly what this is doing. And I actually learned a couple of things while doing that. So let's run through, keep building this out. So we're going to do np.max of qtable state. All right. So what are we doing here? So we're saying if epsilon is less than random.rand and np-max of qtable state is greater than 0, then we want to take and actually I don't even think we need to do the greater than 0. I think it'll automatically just count 0 as a false there. So what we're trying to say is if the table is all zeros, don't follow the table. So here we're going to say action equals np.argmax qtable state. And else, and then else is just sampling from your action space. So when I was talking about, reading, sitting down and actually reading through the documentation, one of the things I noticed is that this np argmax command or statement will grab the first in an array of states or an array of values that is the highest value in the table. So let's talk about what this does. If you have a 0, 1, 0.5, and keep in mind this is 0 indexed. In fact, I'm going to use something, we'll do 0.7. So this is 0 indexed. So the index of the first one's 0, the index of the second one's 1, 2, 3. So if you ran an np argmax on this, what you would get is you would get a 1. So np argmax is going to come back with a 1. In fact, let's just play with it a little bit. So I think this is where it's worth kind of digging into what some of these things are doing. So I'm going to do scratch.py over here. And we will expand this one as well. Let's see. Import numpy as np. And then we're going to do demo is equal to np.zeros. And we'll do 4, 4. All right, print demo. Cool. Yeah, that's fine. It's not set up for my keyboard shortcut on this one, which is okay. So we're just going to run python scratch.py. All right, so we get our little table here. If I then say that demo, we'll do 1, 1, 2 is equal to 5. Well, I didn't print it, so it's not going to give us anything. And you do not have to follow along this part. I'm just kind of showing off what some of this does. So now on the second, so again, 0 indexed, so the second row and the third 0, 1, 2 column, we have a 5. So back in here, if I were to print np.argmax on demo 1, so I'm just going to print out the argmax of the second column. And then I'm also going to print out np.max because we used that somewhere else, and I think that's useful too. Yeah. So you'll notice what we got here is we got a 2 and a 5.0. So the 2 is giving us the index of that 5 on this row. So argmax is giving us the index of the maximum value, whereas 5.0 is giving us the actual maximum value. Now, here's the problem. That we were solving with that if else. So let's say this is -5. -5. All right. So now it's going to give us 0, and it's going to give us 0 every time. And that makes sense, right? It's a 0 table, except this index position we're using for actions. So if we don't code in, so coming back over here to our code, if we don't code in some kind of check to make sure that np.max is not a 0, then what we're going to get, if the max value is 0, we're always going to get the highest, the first value that is the highest. And if the whole table's 0, then our agent will simply take the first value, which I believe is either left or up. So what you end up with if you don't add this and is you end up with an agent that's just constantly trying to go in one direction and it goes nowhere. And that is not super conducive to learning. So we're basically saying if epsilon is less than rand and np.max qtable state action blah 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 env action space sample. And then we need to decrement our epsilon. So if epsilon is less than min epsilon, then we want to go ahead and do epsilon times equals alpha. And that's going to slowly reduce our epsilon. And we can go ahead and just print epsilon. Nope, not episodes, epsilon. Okay. And make sure that that's happening. Okay, so we can see our epsilon decrementing. Now, right now, our agent is still effectively taking all random actions, so we're not really doing anything yet about learning. We're going to start solving that right now. So here is where we start getting into building up our Q table. So the first thing I'm going to do is by default, it does not assign any negative values to falling in one of the lakes. So I'm just going to say if done and reward is equal to 0. So in other words, if we're done with the match, but the reward wasn't anything, then that tells me that we probably failed. So we're just going to say reward equals reward minus 0.1. All right, we're going to decrement reward if reward is 0 and we're done. Then we're going to go ahead and get into the actual Q table estimation. So if reward is not equal to 0, we're going to update our Q table in the state action column and row to equal reward. So if we got a reward, then obviously the value of taking that action in that state is the value of reward. We're also going to assume if we got a reward that next state is the final state. So we're going to go ahead and broadcast the value of reward across the entire row. So if we get to the reward, we're basically saying, hey, whatever we did obviously had a value of reward, and then whatever's in next state has a value of reward. And really this should be reward times gamma. So we're discounting it. Else, we are going to say so if there was no reward, then what we're going to do is we're going to look at the value of the next state and we're going to average it towards the value of our current state. So what this is doing is this first update, let's say we hit this, it's going to make this a reward of 1, it's going to make this a reward of 0.9. But it's not smart enough to do anything else because there isn't actually a reward here in the Q table. So what we're going to do is say that if you got here and moved here, we're going to go ahead and propagate a portion of the value of this state's reward back up. So we're saying, hey, you've got a reward here. We're going to propagate that. And then that will slowly, as we play, propagate back over to our starting position. So we're going to do our else. We're going to do current value equals Q table. So we're going to get the value of Q table in state action. So the action we took. We're going to do the next state value is going to be np.max. So we're always assuming that the agent will take the maximum value in the next state. That's what we're basing next state value on. So doing np.max on the Q table next state is going to give us that maximum next value. All right, and then here's the part to really kind of wrap your head around. So we're going to say that Q table state action, so the value of our current action in our current state is going to be equal to 1 minus gamma. So that's going to end up being 0.1 times next state value. So we're going to grab a portion of next state value plus gamma times current value. And that's really the bulk of the learning here. So let's run this. Okay. Let's see. I still had episodes equals 1. Let's make episodes 100. Something that might be useful, I'm going to go ahead and kill this. I think we know that epsilon is working now, so we can get rid of that print. Let's go ahead and just print off our Q table every single time. So, and in fact, let's maybe not do it every time. Let's do it per episode so that it's not too Q table. All right, so what we start to see here is we start to see it building up negative values. Now, right off the bat, those aren't useful because of our logic that says if max is 0, use go random. So this method does require a certain amount of brute forcing. It needs to get to the end at least once randomly in order to properly build this table up. And you can see it's definitely taking its time getting there. Oh, hey, all right. So now you can see that we have our first value here of all ones. We know that the last state is all ones, and we know that the last Yep. Now these values start to look a little wonky. They get a little big and a little small in some cases. But either way, what we have now is we have an agent that has successfully learned to follow the Q table and get all the way from beginning to end using just basic, a very basic, almost spreadsheet-esque approach to learning its way. So a couple of tweaks you can make, and I'm not going to code these out live, but you can set a human, well, I'll show you this. We can go ahead and just do, reward. Basically, you can set your render mode to none here. We're not going to do anything with reward at the moment. And you can see that finishes incredibly quickly. So it was running slowly because of the human side of it having to sit there and render. But if you are playing with values and you just want to get a really quick view of what's working and what's not, then set render mode to none, and you can see it play the entire thing in one go. If you wanted to, do some kind of just test run at the end, you could do, render mode equals none up here, and then do a second gym.make down here and do a second loop that just pulls from the actions. So there are a few things you could do with this project. I hope what this helped do is helped show a little bit of what the neural network is doing for you. When we say that it's estimating the value of a state, it's not following this exact process, but this is the state estimation that it's, effectively doing. It's attempting to figure out the value of the current state with the next state in mind, with some kind of discount factor at play. Doing this with a table works really well in a simple environment. Like, the reason this works is because it's 16 blocks. If you're playing something more complicated, like even a Pong type game, it becomes next to impossible to show every single state and every single action and to build that up over time. And that's where the power of using a neural net for these types of things becomes really, really helpful. So again, I hope this was useful. If you enjoy, deep learning and this type of content, please hit like, hit subscribe, hang out for more. And then there is also a link to a Discord channel to discuss this and any other projects that you might see on my channel. So with that, I will say until next time.